Peace be upon you and good evening to all students. Today, we continue with the topic, Introduction to Lyotropic Liquid Crystals, Part 2. The pictures on this slide are of the lyotropic phase seen under a microscope. The pictures on this slide are of the lyotropic phase seen under a microscope. This is what we observe under the microscope. The top one is the cubic phase, the middle one is the hexagonal phase, and the bottom one is the lamellar phase. All of these samples belong to me, have been correctly identified and have been published in several journals. But in today's lecture, I will explain these phases but at the molecular level. Lyotropic liquid crystals is formed by dissolving an amphiphilic mesogen in a suitable solvent, under appropriate conditions of concentration, temperature, and pressure, as shown in the phase diagram on the slide. At certain compositions and temperatures we will see different structures. A mixture of soap and water is an everyday example of a lyotropic liquid crystal. The critical micelle concentration, CMC, is the concentration at which micelles begin to form, and it is a characteristic of every amphiphilic system. A micelle is an aggregate, or supramolecular assembly, of surfactant molecules dispersed in a liquid, forming a colloidal suspension, also known as associated colloidal system. A typical micelle in water forms an aggregate with the hydrophilic head regions in contact with surrounding water solvent, sequestering the hydrophobic tail regions in the micelle center as shown on the slide. This is what we call normal micelle or oil-in-water micelle. The symbol is L1. If the solvent is a nonpolar solvent such as paraffin oil, the hydrophobic tail will pointing out to the paraffin oil. This is the reverse micelle or water-in-oil micelle and the symbol is L2. Micellization is a dynamic process. Reversibility. Each second, aggregation number, such as 10 cubed to 10 to the power of 6th monomers are aggregated and about 0.1 to 10 squared micelles are breaking up. An aggregation number is a description of the number of molecules present in a micelle once the critical micelle concentration, CMC, has been reached. In more detail, it has been defined as the average number of surfactant monomers in a spherical micelle. The aggregation number of micelles can be determined by isothermal titration calorimetry when the aggregation number is not too high. Another classical experiment to determine the mean aggregation number would involve the use of a luminescent probe, a quencher, and a known concentration of surfactant. If the concentration of the quencher is varied, and the CMC of the surfactant known, the mean aggregation number can be calculated. Hydrophobic single-tail structures will form micelle at the critical micelle concentration, while hydrophobic double tails will form bi-layer. In this case, we will change the critical micelle concentration, CMC, term to critical vesicle concentration or critical aggregate concentration in general. Vesicles variation and their specifications are as displayed on the right of the slide. Micelles or vesicles both can be utilized as a carrier for active ingredients such as in drug delivery. Micelles only able to carry hydrophobic drugs while vesicles are able to carry hydrophobic and hydrophilic drugs. Hydrophobic drugs can be placed within the hydrophobic bi-layer and the hydrophilic drug can be inside the cavity. Cubic lipid phases can be either continuous or discontinuous. More precisely, a cubic lipid phase composed of individual lipidic particles would be discontinuous, while that composed from interconnected lipid spheres or rods would be bicontinuous. Specifically, a discontinuous structure does not permit long-distance diffusion, while a bicontinuous structure does. Discontinuous cubic phase is denoted as I while bicontinuous cubic structures, denoted as V. Schematic representations of different bicontinuous lipidic cubic phases are presented on the slide. A micellar cubic phase formed when the concentration of micelles dispersed in a solvent is sufficiently high that they are forced to pack into a structure having long-ranged positional, translational, order. For example, spherical micelles a cubic packing of a body-centered cubic lattice. The normal discontinuous micelle cubic phase, type 1, is built up with discontinuous hydrocarbon regions embedded in continuous aqueous medium, namely, normal micellar aggregates in water. The inverted discontinuous micelle cubic phase, type 2, consists of discontinuous aqueous regions embedded in a continuous lipid medium, namely, inverted micellar aggregates in oil. The unique microstructure of a cubic phase offers advantageous properties for controlled drug release. The close packing of the micelles accounts for the marked flow resistance of the phase, which is stiffer than the other mesophase. The cubic phase is formed spontaneously in excess water. Furthermore, the structure provides a slow-release matrix for drugs of varying polarity and size because of its dual polar-nonpolar nature. Additionally, release of the drug from within the cubic phase is controlled to a certain degree because of its unique microstructure. Subsequently, the cubic phase displays bioadhesive properties. Thus, the structure is appropriate for gastrointestinal, pulmonary, nasal, oral, buccal, rectal, and vaginal drug delivery. As a whole, the cubic mesophase is stable in vitro. Hexagonal phase or middle phase can be seen as an array of hexagonally close-packed water layers sheltered by a surfactant monolayer. This phase is analogous to the columnar phase in thermotropic. The long-range order is two-dimensional. Two types of hexagonal mesophase can be encountered: normal, symbolized H1, and reverse mesophase, symbolized H2, respectively, in aqueous and anhydrous organic solvents. The schematic representation of normal, A, and reversed, B, hexagonal phases are presented on the slide. In anhydrous organic solvents, low water content, the structure is reversed and the hydrophilic polar groups now form the inner core and are shielded from the non-aqueous environment by a layer of hydrocarbon chains. These are called reverse hexagonal phase or reverse middle phase. Also, when large quantities of non-ionic surfactant are added to the system, a hexagonal structure and the solution containing reversed micelles may be formed. The hexagonal phase is much stiffer than the lamellar phase. The hexagonal mesophases composed of oleal glycerate and phytanyl glycerate have shown great potential in drug delivery. Lamellar phase, L-alpha, or neat soap phase has double layers of surfactant molecule consisting of polar head groups, which protrudes in the intervening layers of aqueous interface. The hydrocarbon chains are in a dynamic disordered state that is similar to paraffin in the liquid state, and the surfactant layers are separated by water layers. A notable feature of the neat phase is its relative fluidity in spite of high surfactant content, and thus the lamellae can glide easily over one another. Lamellar structure: A, bilayer, B, monolayer, C, rippled bilayer are shown on the slide. The shape and size of given micellar aggregates depend on the molecular geometry of its component surfactant molecules and the solution conditions such as surfactant concentration, temperature, pH, and ionic strength. Control over the shapes gives a possibility to develop and manipulate nanostructures architecture. In this way, exciting functional systems are developed which can find a wide range of technological applications in different fields of science. Preliminary estimates of shape and size can be made with the analysis of the critical packing parameter, CPP. According to Isri-Lachvili, the structure of the aggregate can be predicted from the critical packing parameter, CPP, equals to volume over area multiplied by length, where V is the effective volume occupied by hydrophobic chains in the aggregate core, L is the maximum effective length, critical chain length, and A is the effective hydrophilic head group surface area at the aggregate solution interface. With the increment of value, the structure of aggregates can be spherical, cylindrical, and lamellar. Four vesicles are generally generated, which correspond to spherical, or ellipsoidal, closed amphiphile bilayer structures with an internal cavity containing the dispersion solution. A summary of the aggregate structures that can be predicted from the critical packing parameter is shown in the diagram on the right of the slide. Please visit the link provided on the slide to see the relationship between the CPP and the predicted aggregate. Lyotropic chromonic liquid crystals are formed by molecules with ionic groups at the periphery that associate into stacks through non-covalent self-assembly while in water. For example, copper tetracarboxyphthalocyanine, as shown on the slide, has 4 ionic group which is polar part. In chromonic liquid crystals, the molecules have aromatic rather than aliphatic structures. They are rigid rather than flexible, and planar disc-like or plank-like, rather than rod-like. The hydrophilic solubilising groups are disposed around the periphery of the molecules rather than at one end. The molecules aggregate in solution, not into micelles, but into columns. The driving force of phase formation is phase formation is the face-to-face aggregation of molecules, forming columns, and the geometrical aspects. Phases can be nematic or hexagonal. There are 2 types of molecular shape for chromonic mesogens. The first type is disc-shaped mesogen, as shown the slide. Disc-like molecules are potentially relevant to DNA liquid crystals because both chromonics and DNA are the same type of lyotropic liquid crystals called lyotropic chromonic liquid crystals. In this slide shows the second type of chromonic mesogen. This is lath-shaped. Lath-shaped is having a slender elongated form, like a lath. The slide shows the structures of chromonic nematic and hexagonal phases. Chromonic mesogens can be regarded as being insoluble in one dimension. They tend to aggregate face to face, producing a variety of stacked structures. The classic chromonic phases are the nematic phase. In both of these, the molecules are stacked in columns. In the nematic phase, these lie in a nematic array, i.e. the columns are more or less parallel, but there is no positional order and there is no orientational order of the columns about their long axes. In the hexagonal phase, the columns lie on a lattice with statistical hexagonal symmetry and have long-range order. Apart from amphiphilic and chromonic liquid crystals, there are many other mesogens that can show the lyotropic properties, as shown in this slide. The first is metallomesogen, the second is cholesteric liquid crystals, and the third is amphiphilic peptide. What we can observe is that these three mesogen types briefly have hydrophobic and hydrophilic parts in the same molecule. In principle, it is the same as amphiphilic mesogen, except that there are a few characteristics that make it unique from amphiphilic mesogens. 1. Metallomesogens. Metal-containing liquid crystals are called metallomesogens. First of all, the possibility to obtain mesomorphism in compounds that exhibit geometries which are forbidden for pure organic structures, such as square planar and octahedral. Secondly, the possibility to find new technological applications induced by the presence of metal ions in the complexes such as color, polarizability, paramagnetism. Moreover, the development of bimetallic mesogens constitutes a further step in the field of magnetic and conductive materials, since these types of compounds can exhibit paramagnetism and or mixed oxidation states properties. 2. Cholesteric liquid crystals. Cholesteric liquid crystals is formed by chiral surfactants. In amphiphilic cholesteric mesophases, unlike their thermotropic analogues, the interaction leading to cholesteric behavior may proceed via two possible mechanisms. The first involves pairwise long-range interactions between chiral molecules of adjacent micelles. The second model involves specific short-range interactions between the optical centers of the chiral molecules within the individual micelles. Because of the asymmetry in such interactions, the micelles themselves will be twisted into a chiral shape. 3. Amphiphilic peptides. Peptide self-assembly has drawn a significant attention due to potential applications, especially in the fields of biomedicine and bionanotechnology. The process of self-assembly is based on the spontaneous diffusion and specific interaction among molecules governed by non-covalent bonds, including electrostatic, hydrophobic, van der Waals, metal, ligand and hydrogen bonds, as well as aromatic pi stacking.